All right, let's start with the problem for the night. As usual, I'll read it. Consider the set G of 3 by 3 matrices defined as follows. We define dot as the standard matrix multiplication. Question asks, is G, the set G, an operation dot a group? If yes, is it abelian? Justify your answer. All right, we have already solved quite a few problems of this format. Not that I expect your familiarity with this, it's just that if you wish to go back, view other things on the channel, you can. Right, let's talk about what is a group. So let's start maybe here somewhere. I'm not wasting too much paper. A group is two things: a set and an operation. But is this completely a group? No, not yet. It's only a group if the operation honors 4 different properties: closure, associativity, existence of neutral element, and existence of inverse. Righto. And this is an abelian group if it honors a 5th property. The operation honors 5th property, which is very common and one we absolutely love: commutativity. If this is honored along with these 4, then this is called an abelian group. If just these 4 are honored and this is a set, then this is called a group. Righto. I'm assuming you know what closure, associativity, commutativity, existence of neutral, existence of inverse element is. If you don't, I already have a few videos that discuss easy problems, abelian groups. You can have a look at those. There I describe in much greater detail what exactly is or how we define them and how we exactly use them. Yep. Let's start with the problem. Is it a group? Well, if it's a group, again, we just go through these 4 properties, check if each of these are honored. So let's start with the first one, closure. Righto. What can we say about closure? Well, closure is defined as for all A to B there are elements in G, the result of A operation, which in this case is the dot operation as given the question. Here this is just a random symbol I picked to represent an abstract operation. Here is the dot we have been given the question. This must also be G. All right, that's fairly straightforward. So let's assume an A and B. Let A be an element, and that could be something like 1 0 0 x1 z1 y1 1 0 1, where x1 z1 y1 are real numbers. And we can say let b equal 1 x2 z2 y2 1 0 0 0 1. Then we do this, that is A dot B. If you do this, remember the dot product multiplies this with this. So this would be 1 times 1, x1 times 0 plus z1 times 0. That's just 1. Turns out for all upper triangular matrices being multiplied by upper triangular matrices, all the elements that are 0 are 0. And if there are ones in the principal diagonal, then there will be 1 in the resulting principal diagonal as well. That's just a property. You can actually go and do it for each of these values and you will get these values. But I've used a property here. It's a fairly straightforward property, very easy to prove as well. Something we'll not be covering right now though. So that's something. So that's A. Now let's think about this B. So that's 1 times x2 plus x1. So that's x2 plus x1. All right. Now let's think about this. That's z2 plus z2 plus x1 y2 plus z1, so that is z2, all right, plus x1 y2 plus z1. Now let's think about this and this. For this element, that is 0 times z2 plus 1 times y2 plus y. Well, something you need to understand is that x1, all of these x1 z1 y1 x2 z2 y2 were real numbers. If they were real numbers, if x1 x2 are real numbers, then since addition, multiplication and subtraction are closed already, then this is a real number, this is a real number, and this is a real number, as these are just additions or multiplications performed. And for that reason, a dot b is actually an element of the set G, which means this is actually closed. Righto, that was fun and simple, nothing too complicated. Let's now talk about associativity. I hope that's the correct spelling. I keep botching this up every single time. Let me move this up a bit. Alright, associativity says that for all A, B, and C that are elements of G, A operation, so in this case that is just A dot B dot C should be the same as A dot B dot C. So regardless of your order of association, the result should be the same. So in this case, we're doing A dot B first and then resulting that with dot C, and that should be the same as doing B dot C first and then resulting that, post multiplying that with A. So that really is what we expect. So let's see if that actually works. Now, I'll not do all of this again. Remember, so we can take C to be this matrix, Z3, Y3. I already had A, B in the previous parts and we'll be using that value. So we already know what A dot B is. So we'll call this the left-hand side. We'll call this the right-hand side. We'll do this in a very simple way. We'll figure out what this is. We'll calculate that. Then we'll figure out what this is. Then we'll compare the values. And ideally, they should be the same. And if they are, it's associative. If it is not, then they're not associative. And then we can say that this is not a group. Righto. So let's go. We already know A dot B is 1, x2 plus x1, z2 plus x1, y2 plus z1, y2 plus y1, y1, 0, 0, 0. Right. And then dot C would be this. So this is entirely the LHS. And here we expect 1, x3, z3, 0, 0, 1, 0, 1, y3. Now we already know that this will be 1, 0, 0, 1, 0, 1. This element multiplied by this should be x3 plus x2 plus x1. Alright. Then you have this element with this element. Now this is a really big element, so I'll just write this here instead. So that should be z3 plus y3, x2 plus x1 plus z2 plus x1, y2 plus z1. Yep, that sounds right. And let's look at this. That's 0, that's 1. So this will be y3 plus y2 plus y1. So this is what you get as the left hand side. Obviously, we now need to figure out the right hand side. So the right hand side will look something like A dot B dot C. So I'll have 1 0 0 1 0 1 x1 z1 y1 dot, and we'll do this before 1 x2 z2 y2 1 1 0 0 0. I hope I have the sequences right. Yes, x z y. Sorry, not this yet. And then we have this 1 0 0 1 0 1 y3 z3 x3. I'll do this fairly quickly. I can actually use this space as well. And we 1 0 0 1 0 y1 1 z1 x1. That goes here. I'm so sorry about the background noise. I can't really do much about that. And again, similar business. This goes here, that goes there. x3 plus x2 y3 plus y2 and then that would be z3 plus x2 y3 plus z2. Right. And we'll do this. I'll space these out as I expect the output to be fairly long. And you'll notice that this is x3 plus x2 plus x1 y3 plus y2 plus y1. It's again a long element, and this we expect this. So z3 plus x2 y3 plus z2 plus x1 y3 plus y2 plus y1. If you compare this from the left hand side matrix, this is the same, 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 this is the same. If this element is also the same with its corresponding element, then the left hand side and the right hand side are equal, and therefore this is all associative. Let's look at the left hand side value. So the left hand side value was this. x1 y2 plus z1. Okay, so this is the same on both sides. Z1 can we not find Z1 here? That is unusual. Oh yeah, this is not Y1. It's actually Z1. I'm glad I caught that. Would have been too late to repair it later. So I went like this. Yes, should have been Z1. Anyways, let's go on. Something like x2 y3 exists. Something like z2 exists. Something like x1 y3 exists, and x1 y2 also exists. Oh, wonderful. 0 equal to 0, which is a true statement. Therefore G has dot associative. Right, so we have improved associativity. Now let's move on to the third property. Third property is the existence of a neutral element. This is actually fairly simple. We need to find something. X, Z, Y, 0, 0, 1, 0, 1, alpha, beta, gamma, so that 1, 0, 0, 1, 0, 1, X, Z, Y, yes, and alpha, beta, gamma are real numbers. Well, actually, such so this is the third property you're trying to prove. Such a matrix with alpha, beta, gamma, and alpha, beta, gammas actually already exist, and we know such values which are just 0. because if alpha, beta, gamma are 0, that will make this, let's take more space here, 1 0 0 1 0 1 0 0 0, which is the identity 3 matrix. And any matrix, you know, say A, which is an element G, dot identity matrix will in this case produce, will always return A, which is still an element of G and is the same value as before. So we have proved the existence of a neutral element as well. Now let's move on to the last fact that we need to prove that this is a group, which is the existence of an inverse. Existence of inverse. Righto. So the existence of inverse is, well, we know that you'll have to find an element such that you'll have to find a matrix really that is again of the form alpha, beta, gamma, but this time it returns 1 0 0 0 1 0 0 1 0. Actually, for this you can just set up equations, as also this is the neutral element. So this is what we need on the right hand side. So you can set this up with this, but that's not useful because that just gives you 1 is equal to 1. So let's set this equal to this. That gives you alpha plus x is equal to 0. All right. Then with this would be something like beta plus x gamma plus z is equal to 0 as well. Then you can have something like here, and this would be, my bad, zero beta, so this would be gamma plus y is equal to 0. So basically you can refactor this to say that x is equal to negative alpha, or perhaps you could say alpha is equal to negative x, which is more useful. If you assume alpha is equal to negative x here, so that makes this equal to beta negative alpha gamma is equal to negative z, which says or let's solve the third fact, which just simply says gamma is equal to negative y, and based on that you can substitute values here and you'll get something like beta plus negative xy is equal to negative z, which is the same as saying beta is equal to negative z plus xy. So for given xyz, any value, any arbitrary real value of xyz, you can always find some alpha, beta and gamma so that you can get the neutral element again. And therefore this is also, there's always an inverse element in this multiplication. So we've proven that this is a group because it's closed, it is associative, there's existence of an inverse element, and there's existence of a neutral element, then an inverse element. So 4 things proved. Now let's see if it's an abelian group. So it's definitely a group. We've answered the first part. For an abelian group, we have to check if it's commutative. Let's recall that a dot b was equal to 1 0 0 x2 plus x1 1 0 1 y2 plus y1, and this was equal to z2 plus x1 y2 plus z1. Let's try to find if b dot a would also be the same thing. This would be 1 0 0 1 0 1 x2 z2 y2 dot 1 0 0 x1 z1 y1 1 1 0. And let's do that here again with the property of upper triangular matrix. That's true. And then x2 x1, so let's go, this is x2 x plus x1, this is y2 plus y1, and this element is z2 plus x2 y1. So as you can see, x2 y1 plus z2, sorry, so that was z1 x2 y1 plus z2. If you compare every element, this is the same, 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 this is the same. But this, if you take this out here, you can see z2 plus x1 y2 plus z1, the element here, is not equal to z1 plus x2 y1 plus z2. As these cancel out, obviously, let me make more space. However, x1 y2 is not equal to x2 y1. It might be, in the cases that it is, you have a subset for the group which is abelian, but for this group, the set G dot is a group not abelian. So this is our answer, as it is not commutative. Yep.